So I will just get the partners. The only thing I haven't figured out is if we have an even number of people in here. I haven't looked at that yet. We had 24 at one point, but everything still do. So there might be a situation where 3 people have to get together. So I'm gonna have to figure out how that's fair. What I'm gonna do for that. Okay. So I will give you a partner. You both will get a test, but you'll turn in one stand. Okay. The sessions will be scrambled for each group. Okay. So question 1 for one group is question 40 for a different group. And question 3 for another group is 33 for a different group. This way, I don't want it to be a class test. I want all of you working on number 1 and somebody say it real loud. And I want it to be discussion based. That's why I'm doing this. It'll increase learning and thought process and all that sort of stuff to be able to discuss what you're thinking with somebody else. Okay. You're probably going to be score matched. Not probably. You are. You're going to be matched with somebody who is doing about what you are. My theory behind that is your thinking is similar. Okay. Your reasoning or whatever it is along the same lines. Okay. So that's how I'll be matching people together. It'll be entirely multiple choice. There won't be a written portion since there's 2 people. I think it'll be better. There'll probably be 50 multiple choice total, and that'll be the score. Okay, so you'll both will get the same. Okay, this is kind of something new. Some new research out there shows this is really effective at increasing scores and increasing learning, which is the whole point in the end. So it's another learning activity because it's discussion based. You're preparing for a test and that sort of stuff. Okay, and it helps a little bit with some of you that get test anxiety, that get real, anxious, kind of, a lot of nerves. It might help you calm down a little bit to know you're going to have somebody in your back pocket to help you out. Okay, I'm hoping to give you your pair a week in advance, so you know who you're going to be with. So that way you can even, if you wish, not required, get together for a study session or something like that. Okay, so I'm excited about this idea that came to me. So we'll see how it goes. So that's exam 3. Okay, anything on exam 2 before we move on to PDLs are in process. They're going to be a while. Good. Okay. Urinary system. Okay. Now I want you to take about 5 minutes for this. I want you to just come up with ideas. You don't need to write anything down. Let's see. 3, 2, 4, 3, 3, 3. Okay. So 3. So Rita, Nastasia, Liliana, and Elisha, you 4. That's in the middle group. You 3 there. You 3 back there. You 3 back there. You 3 there. Yeah, you 3 there. Okay, so about 5 minutes. What I want you to do is take on the role that you are going to volunteer in our local elementary school. You're going to work with the older kids, work with graders. Design a science project that will help them understand diffusion and osmosis. Okay, so you're working with kids, so we're looking at straightforward projects here, science fair, you know how elementary science fair projects go. But what kind of experiment could you do for these and help these kids out that would explain diffusion and osmosis? Take 5 to 10 minutes, come up with some ideas. Hypothesize. Go. diffusion and osmosis. Yeah, you all, we're almost done, so you guys can just, Lisa and Brian, know what we're talking about. All right, that was I think enough time. So, okay, so you have a full experiment ready to go?
Yep.
No. Of course, yeah, for 10 seconds. Okay, so let's talk about this little activity real quick. Okay, I had two purposes to doing this really. One, remember the Bloom's taxonomy stuff I talked about way early on? This activity took you to the hardest part of Bloom's. Create your own experiment, right? Some of you, we need to work on create because we pulled out phones and we're looking at Google how to do an experiment on diffusion and osmosis. Okay, so that's fine. That's what we're used to. We have to, you know, as people get used to thinking our own ideas and how am I going to solve things and what materials I'm going to use. I'm working with kids here, so what kind of, you know, over the counter in my kitchen type stuff do I have access to? Okay, so that was one of my goals. Is real this semester. It's more than just science writing. You know, my philosophy is just getting our brains to work, to think, to solve, all that sort of stuff. That was one of my intentions. The second, the biggest goal, as far as urinary system goes, is to refresh your memory on diffusion and osmosis. Okay, so that was the big thing. Okay, so diffusion. The big thing with diffusion is the concentration gradient, right? Things move from a high concentration to low, okay, very easily, quite smoothly. No, I'm not going to do it now. I'll do it in A&P1. I'll describe it to you. In A&P1, we did this activity. There's a few more people in here. There's close recording. The whole class stand up and made them all go to one section of the room. Okay? Everyone's kind of a little hesitant. They weren't quite sure, you know, they didn't want to get too close. So it took me a little energy to like, okay, no, closer, no, move over. It took some effort, okay, to get all the students concentrated in one area in the corner of the room. And then I said, okay, now you can go back to seats. Boom, right back to my seat, okay? That was easy energy, right? That went from high to low concentration. Very easy for diffusion. Same thing in your cells. Things like to go from high to low. Okay? Diffusion, if you add in a cell membrane, okay, a phospholipid bilayer. Okay? In order for things to cross cells, phospholipid bilayers, they have to get either through the cell, or if I draw some cells here, like a simple squamous epithelium, or they have to get between the cells. Okay? Sometimes substances can't do either. They're too big, they're too hydrophobic, hydrophilic, something like that. So something has to help it get across, even though we're going from high to low concentration. That's our facilitated diffusion. It's still with the concentration gradient, but now we have a helper to do that transport. Okay? All right, and then our last type of diffusion, or it's not a diffusion, sorry, transport. The last type of transport, active transport, requires energy. So for me to get the students to go from low concentration right now, spread out, to high, took an energy input on my part and their part to keep, you know, kind of getting closer and closer together. Okay? So these are review concepts, something we would have covered in your biology experience, but are incredibly important to understand well to get down the urinary system. Okay? Okay, so that was just review stuff. Let's get into the urinary system. Starting with anatomy. Okay, I am not going to spend all class on anatomy. We're just going to spend however long it takes. Okay. All right, today I'm going to do slides over here. I'm going to do quite a bit of writing, so I'm going to leave this as kind of a whiteboard for writing stuff. Okay, so the organs of the urinary system. kidneys. Okay, these are kidneys, by the way. On our exam, I got a few, and then I asked you to, or remember, was it the artery or the vein? I don't remember. I think it was the artery. I asked you to identify the artery. I got a few hepatics. So hepatic means liver. Okay, so it's not the liver artery. Artery. Anything with kidney is renal. Renal artery, renal vein, renal disease, renal cancer, renal flow. Renal means kidney. Okay. Okay. So we've got the kidneys, the ureters. So kidneys make pee. They do a lot, heck of a lot more than that. But that's one of the big functions. Okay? So the pee has to get from the kidney to the bladder, where it's held until the time it's convenient to excrete. Okay? To get pee from the kidney to the bladder is these tubes called ureters. Okay? A ureter is kidney to bladder. Then from bladder outside the body is the urethra. Okay? We're going to talk about the urethra a little bit more with reproductive, along with the genitalia type stuff. So we'll get into that a little more then. For now, the urethra takes pee from bladder out of the bladder. Okay? Okay. So those are the organs. Let's look at a little bit of the anatomy of those organs. Actually, I want to do functions first. Okay, here's a giant list of functions of urinary system. Okay, the kidneys in general. There's a lot. Okay, it doesn't just do the pee taking urine part. Blood pressure, hormones. It has to do with red blood cells, makes the hormone erythropoietin. Detoxifying free radicals, so taking them out of the system. Glucose, can synthesize a little bit of glucose. A lot of stuff going on with the kidneys. It'd be cool to address them all, but I really think we're only going to have time. Filter blood plasma and excrete the toxic. So how does the kidneys clean the blood and then get it removed? That's going to take us on Wednesday. We'll be talking about this subject. Okay. Okay. In order to get to that subject, let's start with anatomy of the kidney. Okay, we're going to stay the kidney. We're not going to look at ureter, bladder, or urethra. We're going to stick with the kidney for the next 2 days. So the location, so just real quick, the location is what's called retroperitoneal. Means behind the peritoneum, posterior. So it's not at, your kidneys aren't in your abdominal cavity, it's behind your abdominal cavity. They're in your middle to lower back. Is very, very good. Okay? If somebody has a kidney infection, you can just barely tap, tap back here, and they're ow, it's tender, it's sore. So you maybe have experienced it, you're like, yeah, I know. Okay. That's a kidney infection because it's very tender and very sore. And because that's where the kidneys are at. Okay? And let's look at the external and internal features of a kidney. Okay? So next we're going to add illustration of this. Kidney. All right, so this is really what a kidney looks like. Let's start by adding, we need a bunch of colors here, but it has a little hat on it. Look, I can't reach. The hat's kind of triangular. If I was taller, it would be more triangular. Okay, that little hat is that's the adrenal gland. Okay, so it's not really part of the urinary system. It's part of the endocrine. Right? But we need to know that it's there. It's intimately related or associated with the kidney. Okay. Of the kidney is a layer of tissue. And actually, there, left there. So I can clear this all in. This outside layer of fibrous tissue is a capsule, a fibrous capsule. is on the outside. Okay, important part of holding it in the cavity, in the retroperitoneal cavity. Okay. Anatomy on the inside of the kidney. We've got a couple of sections, okay, that divide the inside. So this is like if I took a kidney and went, okay, not sagittal, not transverse, but frontal section, okay, down this way, okay, side to side, okay. All right. This section is called the cortex, and the intersection is called the medulla. Okay, this is something very easy to flip-flop. I used to do it all the time. Okay, flip-flopping medulla and cortex. Medulla, its word origins is marrow, bone marrow, middle of bone, so medulla, the middle of the organ. Okay, all right. The medulla. Okay, before I get too far internal kidney, let's look external to the kidney. Okay, and like I said, I'm going to add color. All right. As you can see, on the previous slide. The job of the kidneys is filtering blood. So we have to have a major blood supply coming in and out of this thing. So this is the renal artery, and we also have the renal vein. All right, what other tube do I need to add to this area? The color is key, knowing that. Right? So coming out, so all of these three are kind of in the same area. So coming out, oh, this is right, okay. Coming out of that is another tube, the ureter. Okay. This area, this region, zone of the kidney is called the hilum. This is where things are coming in and out of it. Okay. There's probably one more structure I need to add, but I'm not going to for space. So what other item structure? What other structure is here? I'm not going to add this. Part of the hilum. They're smaller than everything up there.
Nerves?
Yeah, nerves. Okay. So we're not going to talk about the innervation very much. It's a time thing. Okay. But the hypothalamus, your brain, one hormones, right? Well, that would be in the blood. Never mind. Hypothalamus, when we're talking about nerve stimulation, the nerves can influence the rate at which we're filtering the blood. Okay, but we just don't have time to do that. All that. So there are nerves here as well. Okay. Okay. So cortex and medulla. So, all right. The cortex has these pyramid-looking deals inside of it. I tried to find like how many. I don't know that there's an actual. I'm sure there's an average number, but I didn't find it. Our cadavers, we always see about 5 or 6 of them. I'll make one more skinny one. Okay? These easily called pyramids. Renal pyramid, okay? But a pyramid of tissue in the medulla. In between pyramids are structures called the column. Okay, it's specific tissue between them called the column. Okay. All right. The ends of the pyramids here have their own name because they have unique characteristics to them. Okay, so all of them have nipples. called nipples. They're called papilla, but papilla means nipple. Okay? So it's a nipple like a nipple on a baby bottle. It's leaky. There's holes in it, like a colander. Okay? So the pyramid and the cortex, but mostly in the pyramid is where the urine is going to be made, and then it drips out of the pyramid, out of the papilla. Okay? When it drips out of the papilla, some other structure has to catch it. Okay? Oh, this one needs a catcher. Okay? The catcher of the first catcher of the P is the minor calyx. Okay, yes. Okay. So the minor calyx are each minor calyx is connected together. Connected together, right, is called the, I'm going to write it over here on this one. This one is major calyx. Okay, so a minor one is at each papilla, and then they start funneling together, connecting, and those are the major calyces, or a major calyx. Okay, so the P goes into the minor calyx to the major calyx. The last section of tissue in the kidney before the P goes into the ureter is called the, you know? I'm going to put an asterisk, you can move it over here and show them. Is the pelvis, the renal pelvis. Okay. All right. Obviously, this image is in your book, but it helps to draw it. Okay, to draw it out. When you're studying anatomy, drawing it yourself is a big help to get down some of the structures. Can you put a major one in there? Okay. So, can we draw it bigger? I just can't see it. It's in the yellow back here. Yeah. Oh, the yellow's not. Okay, you can't see that. Okay. I'll draw it in black. Okay. So the pyramid's coming down like so, and then here's another pyramid, and that's that piece. Okay. So this is a pyramid, and this is also a pyramid. Okay. At the end is the little nipple part, and a minor calyx collects the P at each papilla. But then when those join together, those funnels, those are called major. That help? Yeah. Sure. Okay. So minor, major, ureters, pyramids, papilla, columns, blood supply. The whole point here is to clean out the blood. So we there's blood vessels coming all over this thing. Okay, so I want to show you a picture. So I'm not going to draw you all the blood vessels. And I don't want you to know all the blood vessels. Let's turn that. Where? Okay, so in here, for lecture class, you do not need to know all the blood vessels. You don't need to know the concept that all the blood vessels branch into smaller and smaller and smaller branches, and each branch has a name. Okay? So, aorta coming out of the heart. Renal artery is bringing blood supply into how much? At this point, I'm going to put how much. Okay. Okay, let's do percentage. 21. So in one heartbeat, you have what's called cardiac output. How much blood comes out with one beat? Okay? So obviously that blood is going and dispersed throughout the body. The kidney receives 21% of that cardiac output. That's a lot. For the size of the organ it receives a lot of the cardiac output. Goes with its function. I mean, the whole point is to clean out the blood. So we need a lot of blood supply. So the renal artery bringing the blood in. This renal artery starts to branch out, and they all have names. The blood gets cleaned here in the kidney structure. Once the blood's clean, goes back to the venules, those smaller blood vessels, and then now the renal vein. Okay? That's all you need to know for lecture. This is the concept of branching patterns. Okay? For blood supply. Okay, those are what are called gross anatomy, the large structures. Let's get microscopic. Okay, getting microscopic is the structure called nephron. The nephron, each kidney has about 1.2 million. So you have about 2.5 million of these in your body. That number is just, I don't know, not
Is it all just like in the nephrons?
yes. Okay, the nephrons are the urine making, blood cleaning structures. So that's the structure doing the functions of the kidney. So it's called the functional unit. The functional unit of the kidney is the nephron. Okay, so all right, let's draw the parts of the nephron. The nephron has two major divisions, the renal corpuscle and the renal tubule. I'll draw them and label it for you. And then we'll look at each in much more detail. First, we'll do a broad overview, and then get very detailed in anatomy and physiology of how this thing operates. Okay? Okay, first thing, we have a blood supply going in and a blood supply coming out. But this is all arterial blood. Okay, it doesn't change to venous blood. Blood going in, blood coming out. Okay, blood going in. So this is the blood supply. This is not the nephron yet. The nephron starts with the capsule. Okay, so this is a cross section through this called the glomerular capsule. It's also used to be called by a name, so you'll see it called Bowman's capsule or glomerular. This is kind of the more scientific glomerular capsule. Okay, this starts the nephron. We're at the renal corpuscle is where we're starting the nephron. Okay, the blood supply going into this thing. Okay, so this is a capillary. We're at the smallest blood vessel size. We're at capillaries. Once we get into here. Once this vessel comes into here, okay, it gets smaller, so it's a capillary, but then it makes this giant knot. Okay, the blood vessel comes in here and winds and twists in 3 dimensions, gets all knotted up. Okay, can you draw a knot? I cannot. Cannot. Not. Right? So the capillaries get in there and get all knotted up in there. Okay, it's part of the physiology of how it works. Is it has to get all knotted up. Okay, so the blood travels through here, and then the blood comes back out. Blood going in through this vessel is called afferent. So this is the afferent arteriole. Blood coming out would be efferent, the efferent arteriole. Okay, that's the blood supply. Okay. These capillaries have a name. These are glomerular, or the glomerulus. Okay, refers to the glomerular capillary. Okay, so we'll look at the renal corpuscle in much more detail in a little bit here when we start talking about filtration. Okay, what comes out as far as the nephron of the glomerular capsule? What's our next structure of the nephron? Yeah, okay, yes. So that just, that's not the word I was looking for, but that's right. Okay, so through this description, I'm showing you the renal corpuscle and the renal tubule. So now we're starting with the tubule. Okay? So what I was looking for is what's the first part of the tubule? Proximal. Okay, so the first part is called proximal, meaning closer to. Normally, when you see proximal, not normally, often, when you see proximal and distal in A&P class, what is it referring to? Your limbs. Yeah, it's usually, yeah, closer and farther to, yeah, but usually these are words referring to limbs. Wrist is distal to elbow. Shoulder is proximal to elbow. It's usually a limb description, but here these terms, proximal and distal, are referring to the corpuscle, closer to or further away from when you follow the filter. Keep that in mind. Closer or farther when you follow the filtrate. So I'll show you why. So this is the proximal end, and it's convoluted, meaning it's all folded. So proximal convoluted? No. Convoluted? I don't know what that was. Convoluted tubule. Okay, is the first part of the renal tubule. Okay. All right. After the proximal convoluted tubule, this thing takes a change. Okay, and it goes down. Okay, and then it loops. Stop that right there. Right, I should draw it 100% anatomically correct, but we're just getting the parts down. Okay, so this tubule then takes a turn to go down. Going down, the word is descending. Loop. Does your book use Hamlin? Yeah. It does? It just says loop. Okay. Another thing, the name. Historically, it was called descending loop of Henley, right? But again, this is a name. So it's just scientists trying to get away from names. So you might see this in other references or whatnot, but it's the same structure. Okay? Okay. And then the bottom part actually curves. So this is the loop itself. Loop of Henley. I always use loop of Henley. Okay? And then it curves and goes back up. How it goes back up, though, is right next to these afferent and efferent arterioles. So it comes up through here. And I'm actually going to show it right on through in front of this. Oops, wasn't very straight. So now we're going up. So we have the ascending loop. Okay? This is a little bit different than the way your book drew it. The way your book drew it is they kind of flattened it out to illustrate some of the concepts. But in reality, the ascending loop comes right up next to the renal corpuscle again. Okay, your book folds it this way. And take it over here and take it this way. Conceptually, that's correct. But we need to talk about some physiology that's going on in here. Right? Okay, so that's the ascending loop. Once this ascending loop gets up here, it gets all folded again. Okay? So this is the distal. I'm going to do an asterisk again and label over here because of space. Distal convoluted major part of the renal tubule. The renal tubule will end with a duct over here that has a lot, I don't know how many hundreds, I don't know how many, other nephrons that are joining it. Okay, so this is showing other distal convoluted tubules that are connected with this thing. This is the collecting duct. Okay? All right, so we're going to clean out the blood here, put it in here, and then we're going to, okay, so this is blood. Once the fluid gets in here, that's called, I'll write it over here for space, filtrate. It is not called urine until it gets to the calyces. At that point, it's called urine. The rest of the route is called filtrate, because the filtrate is going to change. Things are going to get moved around. So it's not urine until it's all said and done. Okay? All right, I probably should add one more important thing to this. What would be a really key thing to add? Is that a question?
Yeah.
Okay.
The book said that it was called urine once it gets into the collecting duct. So you're saying don't go off of that, go off of whenever it
Hold on,
gets
let me
to
think
the.
about this. Yes, collecting duct is good.
Okay.
So the final process is in the distal convoluted tubule. It's going to change much. It's going to change much. Yeah. Is that process occurs there? Yeah, it's good. Collecting duct is good. Okay. So one more anatomical structure though that I want to add that is key to how urine's made.
Dr. Sanchez?
Yeah.
So, is it before or after it gets to the collecting duct that it's referred to as urine?
Urine here. We're going to call it here. In the collecting duct.
Oh, okay.
Okay, so so this is a very complicated process how urine's made. And I'm sure you've looked at it with your lunch months, and I'm sure it's all clear as mud right now, right? Okay, so we're going to go through this. You have to understand the anatomy to get the physiology. So I'm going to spend a little bit of time on this. Right? If you don't understand how these things dip and rise and all that sort of stuff, the physiology is more challenging. It's already challenging, but we have to get the anatomy. Okay. One more thing I want to add to this. What's a key part I should add into this description? Matches physiology is why I want to add it. We could do that. We could do the different processes of urine formation.
The visceral layers?
We're going to get there. We can get more microscopic and look at the different layers. Think about the kidney itself. That's what I'm getting at.
Where is this happening within the kidney?
Mm-hmm.
Like between the cortex and the medulla?
Yeah, so we need to add the cortex and the medulla. So where do I put them? Where's the cortex and medulla on
Well,
this
the
drawing?
one is there's two different types of nephrons.
Yeah, we'll call this juxtamedullary. Most of what we're talking about for the next few days is the juxtamedullary nephrons. Okay, so I'll add it. Right. Let's see. About my collecting duct's a little high. No, that's good. We'll put it right about here. Very straight. It's supposed to be straight, but I need to make sure you understand this concept. The renal corpuscle is in the cortex. Okay? So, how am I going to do this? Like this. Watch this. Cool thing. Over here. Renal corpuscle, okay, our little C cup thing, and our glomerulus, our knot of vessels in there, is in the cortex. This loop that moves down and then comes back up is like that, right? So the cortex, the renal corpuscle is up here, and then the loop goes down into the medulla. It's important for how urine's, all these processes of moving stuff in and out. Okay? so how's that drawing? Again, the drawing's in your book, but draw it out yourself to really get down to the structures. Okay? All right, let's look at the renal corpuscle in much more detail. All right, I'm going to start with the book's picture. Not that one. The next one. Okay, this is your book's picture of the renal corpuscle. I'm going to redraw some of this to illustrate some concepts of how blood's getting cleaned out, filtered. Okay, first of all, the blood capillaries going into that thing are all knotted up, right? And so what this picture is showing is that you cross-section through it, you can see that there's a large blood supply in there. And we're microscopic. Remember, we have millions of these. Okay. Make sure I'm doing this in order. You with me? You with me? We haven't got to the hard stuff yet. Okay. Right? Right. Okay. The renal corpuscle. This is where cleaning the blood starts. Doesn't end here, but it starts here. What I want to illustrate is the anatomy. The capsule and the capillaries are associated with each other. So I'm going to draw a red blood vessel, capillary, like so. Okay, so let me make sure you understand. This, I'm trying to draw what's inside here. Okay, so it's a capillary. What I want to show you is the visceral layer of the glomerular capsule here. So on this image in your book, it's this all in here. See all these squiggly lines? That means something. And I'm going to show you what that means. Okay, it's not just squiggle lines. They're trying to illustrate a concept. Okay, the cells of the visceral layer are called podocytes. What does podo refer to? Meat. Okay, so how these cells look is they have all these extensions coming out. Okay, draw. Practice this a lot this weekend so that it will not look so crazy. It's already going to look crazy. What in the world is what? The starfish. Okay, nucleus. Okay, so here's one cell of the visceral layer of the glomerular capsule called a podocyte. The way podocytes operate is the cells interdigitate. Okay, so if I draw another cell over here, I can draw its little extensions, kind of go next to.
So they're not all necessarily connected?
Right, okay, and here's nucleus. Okay, and then you can, I can't draw in 3 dimensions, but you can imagine this is wrapping around, right? So I can draw another extension that's coming from the cell on this side that's kind of wrapping around this blood vessel. Okay, so these cells have these foot-like extensions, and these are called a pedicel. Okay, this is important to understand the first concept of cleaning out the blood. So you can see all these gaps in here. This is intentional, right? This is how the structure is put together. These gaps between the cells of the visceral layer. Those are called slits. I mean, technically they're called slits. Whatever. It's a space. Okay? Okay, so that is the renal corpuscle. Done. Okay. Let's look at one of the pictures, another picture from your book. This image here that your book has is the same as what I'm kind of trying to illustrate here, okay? Your book has the blood vessel here, so this is bloodstream in this purplish color. I don't know why it should be red, but whatever, okay? This here is blood supply. This side here is the cup, right? The cup that goes over the blood vessel is that side of it. So this, the space, the capsular space in there, okay? This is cells of the blood vessel, of the capillary. This is the pedestal of the podocyte. Got that? I don't know if you're relating all that. You get the orientation down of what I was trying to show you, and what this shows you is different cross sections. Okay? Okay. The reason I bring this up is to show you all the gaps. Okay? This capillary. You make sure the answer is not on the board before I throw it out there. This is a special type of capillary. What type of capillary might this be?
Renal.
Very good. I like it. Partial credit. Yeah, all right. Somebody got it. Fenestrated. Remember that word? Fenestrated capillary? What does fenestrated capillary mean? Pores. Okay. When we did capillaries in chapter 20, showed you pictures of 3 types of capillaries. What were they? One, fenestrated. Most of them are called continuous. Okay, remember the pictures of the capillary. I'm trying to tie chapters together, okay? Concepts together. Here it is for you. Okay, that was kind of neat, huh? Just give it to me at the beginning. We're not going to think. All right, here is a picture of the fenestrated capillary. It comes out of your textbook. This is out of chapter 20, okay? Showing that the epithelium, the epithelial cells of the endothelium, right, insides of the endothelium, have these spaces between here, the pores, filtration pores, okay? So the reason that relates to now urinary system is that's the type of capillary we're talking about in the renal corpuscle, okay? So you can see here now the pores. Here's a filtration pore between the red blood cells, okay? And here are the slits between the podocytes, the pedestals of the podocytes, okay? So we have a very leaky system here, very, very leaky. Needed to make urine, to clean out the blood, okay? Okay. That's what I just showed you. Okay, here is the drawing of your book of the nephron, which I just drew. They're exactly the same, other than I moved this distal over here because that's the way it really should be shown. Okay. They books, not just this book, do this for concepts that explain how urine's made. But there's some anatomy and physiology that they should draw it over here. But you can see how you fold it all up. See a mess. Okay? Okay. So that is the anatomy that we're going to go through. Okay? Let's get into making pee. Okay? Y'all had coffee this morning, right? And now I'm talking about pee. You're really learning how math section is to the rest of your class. Okay. Urine formation. Alright. So here's the learning outcome, learning objective. We're getting into how does the nephron, the kidney, all this together, clean the blood. Okay, so cleaning the blood is filtering it. You have to understand the cellular structures to know how this all works. Okay? Okay. All right, let's first just define all the process of making urine. Okay, so let me draw. This is not exactly in the book. Anyway. Nuclei. Okay. And then I'm gonna draw some more cells. These are orbital cells. Oh, there goes the mark. Oh, very even. Nuclei. Okay. This is blood. There. Going through this blood vessel. This is the tubule, so we're talking about filtrate. Okay? So between the blood and the filtrate would be space, but it actually has a name and it's actually a functional name. This is interstitial. Interstitial space, which just really means tissue space. Okay? Okay. In order to properly and fully clean out the blood, you got to do it a few ways. Okay? First, we got to take blood stuff and get it over here into the to become filtrate. That process is called filtration. Okay? That's how you make filtrate. It's taking blood, lots of blood things, and getting them over here. Okay? But that process is non-specific. The only thing that controls that process is size. If it's a large thing, like a red blood cell, it's not going to go into the filtrate unless you're unless there's something wrong with the kidney. You can get blood in the urine, but something's wrong. Okay, the kidney's diseased, injured, trauma, something's going on that's not supposed to. Okay? Okay, so we're just going to put everything over here that can fit. Well, a lot of it we actually want. We don't want it over there. So we got to take it back. We're going to take it from the filtrate and put it back into the blood. That process is called reabsorption.
And what's back over there?
Things we need. Things that are not waste. Glucose, a lot of minerals, ions, water, things we need to hold on to. So basically, I'd summarize that as not waste. Okay. But we also have one more thing in order to fully have this blood cleaned out. Is sometimes there are specific things. I just want to call it things right now. I don't want to get too overwhelmed with detail. Toxins, proteins, some nitrogenous wastes, and some specific stuff that needs to get the blood into the filtrate. Okay? So these processes are different based on specificity. Non-specific, based on size. If it's big enough, it's going to go. Very specific. Specific transporters to move stuff from here to here. This process is called, I know you know. What's this third process called? I'm sure you've done the process. Thoughts, ideas, something you should. This is secretion. Okay? We're secreting stuff from the blood into the filtrate. All right, and then the last thing, which we are probably not going to run out of time to talk about, once the filtrate has gone through all these processes and gets into the collecting duct, call it urine, the final process for this, oh, you guys don't like to write it, I'll write it big. Excretion, we won't use this one. Excretion. Okay, so this is fully the process of cleaning out down the blood and then removing the waste from the body. Filtration, reabsorption, and secretion.
And that just happens between the two people in the blood vessel.
Yes, we're talking about not only the tubule, the whole thing, the whole nephron. So between the nephron and the blood, things are going back and forth at different times in different manners. And you look at all that happens. Okay, let's get into start filtration, and I don't see. I'm not going to speak. Step on my gas pedal right now and to knock it out. We're not going to get through filtration today in class. So on Wednesday, we will do filtration, reabsorption, and secretion. Let's start filtration. And I'll see how much I get through. Okay. Oh, let me show you this. What I just drew here, it's small because it's in your book. I'm not needing to use it right now. What I just drew right here, the same thing is laid out right here in this image. Okay, so I tried to recreate it in my own kind of way this way. Okay, so they're the same thing, showing you filtration, reabsorption, secretion, removing stuff out. All right. Okay. In order to start this description, we'll jump up at once now. I'm describing this thing. We gotta do some math. Pressure. We gotta look at all the pressures in the glomerular capsule, the renal corpuscle itself. Okay, there are different pressures in the capsule itself. There's blood hydrostatic pressure, capsular hydrostatic pressure, colloid osmotic pressure, and those are the big ones. Those are the ones we're going to talk about. We skimmed over these when we were talking about capillaries, but now we need to look at them in more detail. Okay, so I'm going to bring up the capillary picture to jog your memory that we kind of did briefly cover these, but I skipped over it pretty quick. Okay, this is a general capillary for circulation, and this is showing filtration rates because of different pressures. Like hydro means water. Okay, so the water gives a certain pressure. In a capillary, the hydrostatic, the water pressure, is higher in the capillary. Okay, so that gives it a net pressure, forcing outward. So the water goes out. Solutes go out as well. Okay. Also, hydrostatic pressure, though, from the tissue. The tissue has water in it, so it pushes back. Okay, so you have this hydrostatic from blood, hydrostatic from pressure. From tissue. Hydrostatic from tissue. Okay? All right, that's hydrostatic pressure. In the blood and in the tissues are proteins. Proteins contribute their own pressure. That's called the colloid osmotic pressures. Okay? So the proteins from the blood, it's actually more of a pull than a push. The proteins from the blood give pull for pressure, and the tissues give a pull on the pressure. So you can go and measure those all out and see the differences between them all. In a normal capillary, it lets you know how fast things are going to be filtered. A filtration. Well, let's look at the filtration in the renal corpuscle. Okay, so like I said, hydrostatic pressure from the blood, hydrostatic pressure from the capsule. So if I draw this real quick, I got a capsule. Oh, that's not the capsule. That looks like a kidney almost. okay, the capsule, and then the blood coming in. Blood vessel in, blood vessel out, okay, and then the knot of capillaries that's happened in here, okay? Okay, so the blood in here, some of the water forces this way, but the capsule forces back that way. The blood forces pressure, the blood pressure is at, on this side, is about 60 millimeters of mercury. The capsular water pressure is 18. I don't know why I got 32. 18 millimeters of mercury is forcing back up against it. Okay. You also have proteins. The blood has proteins. Capsular fluid, the filtrate, does not have much protein to speak of. So you do not have colloid osmotic pressure from the capsular side. You have it from the blood side. Okay? That's where I got 32. The 32 millimeters of mercury is the colloid osmotic pressure. Okay? All right. So you can calculate what pressure going on here. We do 16 minus 32 minus 18 is that's 40, 50, so that's 10, right? All right, yeah, 10. Well, I'm using different colors. I guess I should 10 millimeters of mercury. So there's a net pressure pushing water into the capsule. Okay, yeah, Lisa.
So 60 is pushing and 18 is pushing out and 32 is pushing.
32 is more of a pull. So it's the pressure's from here, but it's more pulling it this way. The proteins are in the blood. So this is it's more of a pull against it. Okay? But the net is 10 millimeters of mercury.
So would that be considered a negative pressure?
It depends. What's the negative? The 10?
The 32.
The 30, yes. Yes, because you're opposing hydrostatic. Okay, so I'm going to say one more thing before we go, and we'll pick up with GFR on Wednesday. So that means this pressure influences, oh, I should probably say two things. This pressure influences at the rate the blood filters. That's called glomerular filtration rate. Glomerular filtration rate. The amount, which is the amount of filtrate made per minute of the two kidneys combined. Okay? So, every day, you make in your kidneys 180 liters of filtrate. How much blood do you have? And Mary, between 3 and 5. You have in your body 3 liters of blood. You make 180 liters of filtrate. That means in the nephron, we need to get back almost all of that. Right? Because you don't pee out 180 liters a day, right? No, God. That would work so well. Okay? All right, so we're going to look at glomerular filtration rate on Wednesday. How do we do the reabsorption? And how do we maintain